Well, greetings to the snow day video. Very exciting stuff. So I got a lot to share with you today. I use a variety of formats. So first of all, here is a problem that illustrates the method of Lagrange multipliers and a kind of problem you probably wouldn't have seen in Calc 3. So here's the question. I've got two spheres with arbitrary centers, P1 and P2. The question is to find points on these two spheres which are closest, given, here's the definition of a sphere, right? The set of points equidistant from the center point P. So here's kind of a picture. I'm trying to minimize this distance d between the 2 points. Let's call it x vector and y vector with coordinates x, y, z and coordinates u, v, w, right? So, of course, it suffices to minimize the squared length between these points, right? Which is, it gives us this formula here. That's my objective function. I'd like to make it small. So here's the new idea, perhaps, is that we can look at this as a problem in R6 with variables x, y, z, u, v, w. And two constraints, right? The constraints are that, the x vector has to lie on the first sphere and the y vector has to lie on the second sphere, which gives me these two equations in 6-dimensional space, all right? Now, so the method of Lagrange multipliers, in this case, in this context, gets two multipliers. All right, so like here are the multiplier equations. The gradient of f is equal to lambda 1 gradient of the first equation plus lambda 2 times the gradient of the second equation. Now, here's what I mean by gradient in this context. It's a 6-dimensional vector with x, y, z, u, v, w derivatives. And so I take these gradients. The objective function's got everything going on, but the gradients of the equations here, g1 and g2, those the level functions, they're pretty sparse. They've got zeros in the one spots that they're not about, so the first sphere only gets non-trivial components in the variables which correspond to the point on the first sphere, whereas the over here only the components corresponding to the second sphere get non-trivial components. So all said, we get these Lagrange multiplier equations down here, paired of course with the constraint equations. We always have to solve all of these simultaneously. And I did try to just straight solve these, and I may just be distracted today. I couldn't quite solve them like directly. I feel like, that may be, just me today. But of course I can describe the solution geometrically. It's evident from the outset. Like, you can kind of tell what the solution is to this problem anyway, even without Lagrange multipliers, which is why I believe the algebra should actually work out somewhat easily. I don't see it explicitly yet. I'm going to show you some examples where I do have the algebra worked out to the bitter end, but they're not as pretty as this. So anyway, so I'm keeping this example even though I don't have all of the algebra. But here's what you'd have to do, in my opinion. This should be the answer, is that it's going to be the line that connects the centers of the two spheres together. That line which connects them, it should pick up on the points which are, closest together, and it should lie along the line which joins these two radii of the two different spheres, right? And so basically you just look for this line of intersection. The line goes from P1 to P2 as I've set it up for t, ranging from 0 to 1. And then to actually find the solution points, I just need to find intersection of that line with the spheres, which I attempt to do down here. And I hope that these actually, what I boxed, if you were to go sort through it, I think these actually would solve the Lagrange multiplier equations, but admittedly my current solution's incomplete. But again, I didn't want to give up on it because I just think this is a cool problem I want to show you. So, L of t intersects the first sphere. That means that if I plug the parameterization of the line into the defining equation for the sphere, it has to work. But that makes the P1 be canceling, and it just leaves you with, you can solve for time. Of course, there's an absolute value going on, so I have a plus or minus, and I get that time for the time at which the line intersects, x over here, that point of intersection, I think. And then on the flip side, if I look for the point of intersection of the line with The second sphere, the algebra is a little bit different because the p1 doesn't cancel, but it's not too bad. You end up with it like an absolute value t minus 1, and I got these time solutions. I don't know why I was thinking about putting a t tilde in there, but the t plus and minus are different from the different boxed equations here. You guys can understand that. I think I don't need to start putting tildes on everything. All right, anyway, get into it. So this is the other times the line intersects the other sphere, which gives me this is the point of intersection. Now, there's a plus or minus here. That makes sense as well, because if you think about it, the Lagrange multipliers should pick up both on the points of closest approach, but also in like the points which are furthest away, which are going to happen here and there. So I think it's picking up on all of that. But anyway, just wanted to show you that. That's an example of how the Lagrange multiplier method actually works when we have, you know, like more constraints. Now let me see if I can turn off the light over here maybe and zoom in a bit, or maybe I need to zoom this in. Sorry, it's kind of awkward. I'm holding the laptop sideways, but I think it's going to work. So these are some problems that I assigned in advanced calculus back in the day when I first used Edwards as the text. So if you ask me ahead of time, I can bring Edwards to the office and you can look at it. Or you can spend like $10 to get yourself your own copy because they're like super cheap. It's a Dover book. Anyway, so just wanted to just glance through these solutions. I'll try to post the PDF of this thing in like Canvas once we're done here. But here's a nice problem. You have a rectangular solid. Find the one of largest volume inscribed in the unit sphere. So you let xyz be a quarter of the solid, and octant 1, your volume is 8xyz, that's your objective function. And then the constraint is that xyz is on the sphere, which is that this is equal to 0. Here there's just one Lagrange multiplier. This problem, of course, you may well have seen in like Calculus 3, for example. Turn off all the lights here for a second. There we go. Yeah, so there's that one. So then you solve these equations, and out pops the origin or the interesting solution, which is that x, y, and z are all equal, which kind of makes sense because the symmetry, the problem, the cube forbids any distinction between x, y, and z. So you could have guessed the answer here anyway. Here's another problem. You got maximum product of sines of 3 angles in a triangle. So your objective function is the product of sines. You know that the sum of the interior angles in a triangle is pi. So lo and behold, here's your Lagrange multiplier equation. And you can divide these equations and get tangents are equal. And so you get all the tangents are equal, which then forces the sum of the angles to be pi, which means that by the symmetry, it's an equilateral triangle. All right, well, yay. Anyway, all right, so let's get on with it here a second. Here's the points on the ellipse which are closest and furthest from the point 1, 1. I'm not going to we talked about that in Calc 3. No need to talk. Oh, that one's ugly. That one might not work out well. Let's skip past that. Okay, again, just one multiplier. Let's skip past this too. I'm going to post this PDF. If you're curious about these, you can look at them. All right, still just one multiplier. Let me go past this. Ooh, it's got variables in it though. That's exciting. Let's see here. All right, finally, we have 2 constraints on this one. We've got it has to be on this plane and that plane, and our goal is basically to find the points on these 2 planes which are closest. So to do that, we have the objective function. I think it's no. Wait a minute. Wait. Find the points. What is the question here? I'm trying to find the point closest to the origin, I guess, that's on both of these planes. The point, I guess it's the point on the line of intersection of these 2 planes, which is closest to the origin. Must be the original problem statement. All right, so the objective function is that. These are my constraint equations, which are surfaces, indeed planes here. And as such, I have 2 Lagrange multipliers, and I get these equations, which you do some algebra here, all right? You do some more algebra, eliminate stuff. You don't care about the lambdas. You really want to get rid of the lambdas. We finally get to this equation 1, And then I plug it in, I find the lambda 2, plug it back in, get an equation 2, and then I take equation 1. I do a bunch I'm sure this algebra is not minimal, guys. Like, it's just algebra. So after some algebra, I finally find that the solution to these equations is 1/7, 12/7, 3/7. So, all right. Anyway, my point to you is simply this, that when you're up against the Lagrange multiplier algebra problem, you know, it may or may not be super easy to actually do the algebra. In fact, the algebra is usually the actual hardest part in all this. Like the setup, once you understand this trick of multiple multipliers, it's pretty standard, the setup. So, yeah. Let's see here. Oh, continued. Oh, wait a minute. No, this is... Oh, yeah, I used to assign multiple book problems for one problem. See, I'm so much more mellow now. All right, so here we've got a cylinder and a plane and an objective function of z. I think we're looking for the point on the intersection of we're looking for the point on the intersection of the cylinder and the plane, which is at the highest z. All right, so, or maybe the lowest z, I don't know. I keep losing my cursor, it's hard for me to see. Oh, there it is. So I've got two constrained equations, which gives me these two gradients, and lo and behold, of course the objective function's easy this time, 0, 0, 1. These Lagrange multiplier equations look like more appropriate for like a test. It's the first problem I've looked at and I've gone, you know, this would make a decent test question because it's not so horrible. So you could do the algebra here, and after a bit, you find 2 points. All right, that and that. Of course, one is the highest and one is the lowest. And there you go. It's also kind of obvious if you think about the intersection of a cylinder and a plane that there has to be an answer because that intersection is compact. So it makes sense that there would be an answer. Here's another one. Let's see here. X plus y is 10. U squared plus 2v squared is 1. I'm setting up constraints in four-dimensional space, x, y, u, v space. The objective function. So what we're doing is we're looking for the point on the line. Let's say y equals 10 minus x, and the ellipse, you could call it x squared plus 2 y squared equals to 1, which is closest. So we're using x and y for the line coordinates and u and v for the ellipse coordinates, and treating them collectively as two equations in a four-dimensional space. The reason we're introducing u and v versus x and y is to separate the coordinates on the line from the coordinates on the ellipse, which are, of course, logically distinct. So then you set up the Lagrange multiplier, and it looks like this. And then, as per usual, you do a bunch of algebra, eliminate stuff, and you find, in this case, 4 solutions, and you can sort through which one's the correct one there. All right, let's see here. Then, next problem. Here's find the points of the ellipsoid, which are closest and furthest from the plane. So this is kind of like the one I started today with, which is you use 6 dimensions, x, y, z for your first surface, and u, v, w for your second surface, and your objective function. In fact, this objective function is the same one I started class with today, right? And so we got these 6-dimensional gradients, we got Lagrange multiplier equations out the wazoo, and you can solve them. And after you do, you get these lovely points down here. So, oh, and I guess that's it. So maybe I solved that problem. Maybe I kind of got stuck on that one too. I'm not sure at the moment, just glancing over it. I just wanted to share these with you just so you have a little bit more texture in the Lagrange multiplier examples. I mean, I'm happy with what I did last class because I think, you know, it's very important for us to understand the underlying geometry of the problem, and I think we did that last class. But it's also good to see some actual ugly examples. I think I've achieved that. All right, so moving on here. Let's see. So I have 2 remaining things I want to do today in this video. The one is to give you a massive review or perhaps introduction to some problems in linear algebra. And the other is to mention a problem in the current notes that was pointed out to me by Preston, there is a spurious transpose in an important theorem, and maybe I'll start with a typo. I think that's probably where I should start. Then we'll get to the linear algebra. If I can find my notes, that'd be great. Of course, I have a list of other typos I need to fix, which I will hopefully get to sometime soon in the midst of all this nocation. All right. And anyway, so here we go. I turned on the lights. I should have turned the lights on. What's wrong with me? Oh, here we go. All right. So let me go back a bit. Back in chapter 4, back before we got to Lagrange multipliers, when I was still talking about tangent spaces and normals. Not that one. I'll find it eventually. Maybe I should make this page smaller. Alright, let's see if I can find it right quick. Alright. Theorem 4.24, k-dimensional level set. I say let me make this bigger. Come on. Alright, double scrolling, don't you do anything to me. Alright, so down here we have a level set with these, defining level equations. The level function, let's call it g. I said the gradient of the component functions are perpendicular to the tangent space at P. I need the transpose here because, see, goodness gracious. I guess it depends on whether or not I'm thinking of the gradient vector as being a column vector or a row vector. I think there's a good chance I'm inconsistent on this point. Overall, I need to, probably the notes overall have an inconsistency there, because I think sometimes I put like transpose, if you go back to where I introduced the gradient, the Jacobian, back over here. And back. Where did the Jacobian enter the scene here? Oh my goodness, even farther back. Where did I first introduce the Jacobian? Probably should be around here somewhere. Let's see here. All right. Yeah, so I said that the gradient is a column vector back here. Yeah, that's fine. You could either say the gradient's a row vector or a column vector. I'm saying it's a column vector there. And for that reason, I have to put the transposes over here to be consistent, right? Because otherwise, I can't have a column vector be a row, so I have to take the transpose of the gradient vector to get the row vector there. So if I go back over here to chapter 4, and I look back at theorem 4.24 once more. I think it's down here. Where'd you go, theorem 4.24? Oh, there you are. I'm saying that the gradient vectors are perpendicular to the tangent space at P. I do not need this transpose here because the gradient of Gj is already defined to be a column vector. So this transpose, it belongeth not here. All right, because I'm working with column vectors paired with points. All right, just to be fussy, that should be a column vector, and indeed it is already a column vector because I defined the gradient to be a column vector back in chapter 2, and I can't just willy-nilly change that now. All right, so that's one thing. I need to fix that. That was not what Preston was fussing at me for. And of course, Preston wasn't really fussing at me. I'm just putting words in his mouth, but that is my right. So, yeah, sorry, I should behave. I think it was this one that was more offensive. So here we have the tangent space at P is the null space of G prime transpose. See, I this transpose here I do not believe belongs here. And the reason for that essentially is the same as what we were just talking about. If you look at when I actually calculate the tangent space from the null space, you'll see I don't really adhere to that transpose. Like, let's look at the next page. See over here? If you look at this example, for instance, I've got little g. I mean, why have a big G? That would make it easier for the students to understand. I'm still talking about the same idea. You got to change the notation when you go from the theorem to the example. Otherwise, the students will not be confused as you want them to be. So you got to change the big G to a little g. That's just, you know, good pedagogy. So that was sarcasm, just to be clear. So let's see here. Yeah. So in this case, there's just one level function, the gradient. So this is sneaky notation. That's actually a column vector. And yeah, so I plug in the point in question, which is 2210, and that gives me where's that thing gone to? This down here, 4 minus 4 1, and see, I want that to be 0. It's kind of hard to see here, but that is just the first row in the Jacobian matrix for G here. I guess we can't see too much. Let's go on. But again, I would argue the transpose is not there. Maybe it's more clear in this example. See here, this one, you got two equations. And if you look at the calculation, I guess gradient G1, gradient G2, right? To try to find the normal space, I'm looking for the normal space to the perpendicular to the normal space is the tangent space. So I'm looking for, and of course we know that the gradient to the level functions give us the normal vectors. So these are the normal vectors, and I'm looking for vectors which are perpendicular to those. You notice that there's no transpose in here. It's really, this literally, if you break it down, it's just the calculation of the null space of the Jacobian at the point. So there's no transposition going on there. That transpose in theorem 4.25 for the null space does not belong there. It's even more manifest here. This is the Jacobian at the point in question, and when you calculate the reduced to echelon form of it, you get this matrix, and this standard calculation down here is the standard calculation to find the basis for the null space of that matrix, which evidently is a basis for the tangent space at the point. All right, I'm going to explain more about this null space and calculation in the piece that follows here. I just want to make sure I've chased down all my demons in terms of the transpose here at the moment. Over here, I don't have a transpose on this one. Well, anyway, I'm gonna think about this some more, whether or not that actually belongs there. I think that one belongs there, but we'll see why eventually here today. Okay, I think that's pretty much all I wanted to correct at the moment. I will actually make a correction to the notes and repost it. When I do, of course, I'll let you guys know. Yeah. All right, so let's talk about linear algebra. If I can find my... Oh, this is the problem with not having class, is I spend 2 hours creating notes for class, and then I make a video. All of a sudden, my work for today has become, instead of a 1 hour thing, a 3 hour thing. And then I never know whether you guys actually watch the video or not. So it's very kind of unsettling. Honestly, I detest snow days. They just make way more work for me, honestly. All right, let me have a sip of something here. Ooh, yowzers. Whew. All right, so let's talk about the linear algebra we need for advanced calculus. Sorry about I see that there's a bar in the video. This particular frequency of these lights, it kind of makes a visual oscillation. I don't know which one it's doing it. Maybe it's this one. Let me try turning this one off. No, that didn't do it. Is it this one? Is this the offender? Might have been that one, actually. Maybe it was that bulb. All right, I think that bulb was the offending one. All right, cool, we got it. All right, so first up, so like here's what we're gonna do. I'm gonna spend about a half hour, hopefully, and I will go very fast, so you can pause as needed. But my goal here is simply to give you a quick overview of the part of linear algebra that we actually most need in this course at the moment. So there really are two things that we keep doing. One is to calculate the null space of a matrix, and the other one that we're on the cusp of doing more, actually we're kind of done with it in some sense, is the eigenvector thing. But anyway, so here we go. So given a matrix, the null space is simply the set of all vectors that when you multiply them on the right of the matrix, you get 0. So this is called the null space of A. The main theorem to know about here is that the basis for the null space can be derived from the reduced to echelon form of A. In particular, we can write each pivot variable as a linear combo of the non-pivot variables as to identify the spanning set of linearly independent vectors for the null space of A. That is, a linearly independent spanning set is to say a basis. All right, that is what a linearly independent spanning set is. It is what we call a basis, all right? Although technically a basis is also ordered, but let me not distract us from the main event. So here we go. Here's a matrix A, it's a 2 by 4, and I made it easy on us. This is already in reduced to echelon form, all right? So the pivot columns are the ones which have like E sub 1, E sub 2, or E sub 3, but this only has E1, E2, so you can only have as many pivot columns as you have rows. If I've got 2 rows, I can have at most 2 pivot columns. I have 2 here. The non-pivot columns are the second and the third. All right, so the pivot variables are x1 and x4 in this context, if I write it like that. So I can write x1 as minus 3x2, minus x3, we put minuses because this first one actually corresponds to like an equation, x1 plus 3x2 plus 3 plus x3 equal to 0, or this one corresponds to the equation x4 equals to 0, which I have written over here. I'll expand on this more when the example is a little bit bigger so you can appreciate it more, like the next example, okay? So if you didn't quite follow why I put this and that here yet, don't fret. But it is a pattern that you hopefully can batch. Then we simply plug those into the vector, which means x1 and x4 get the equation, in this case, minus 3x2 minus x3, and 0. No further simplification should be needed, by the way. You just plug the equations that are evident from the reduced to echelon form into the vector, which is in the null space. And then when you do that, you will always be able to factor out the non-pivotal variables as parameters in the solution set, in this case x2 and x3. And the vectors which remain by the structure of row reduction have to be linearly independent, and as such will give you a basis for your null space. There's more here though. The vectors in the null space actually have to be perpendicular to the rows of A. Like, check it out. If I take the dot product of this with that, I get 0. If I take the dot product of this with that, 0, 0, 0, 1, I get 0. The dot product of minus 1, 0, 1, 0 is this with that is 0, because minus 1 plus 0 plus 1 is 0. And of course the dot product of this and 0, 0, 0, 1 is 0. So the vectors which form the basis for the null space are by necessity perpendicular to the rows of A. So we have this equation, like the perp of the row space is the null space. Or of course you could also say that the column space of A transpose, which is by the way the row space, because a transpose has each column the same as a previous row and vice versa. Let's see here, I guess we could take these equations and write them for the transpose of A just the same. All right, I'll try to do that. I don't want to ruin this, but so if these identities are true, it's also true that the null space of A transpose is the perp of the row space. Man, I regret this. A transpose. I don't know if you can see that or not. And let's see, I'm going to go over here instead. So A transpose is A again. So the column space of A perp should be equal to the null space of A transpose. So I think that may actually be a relevant thing to know for the purpose of understanding the normal space for the tangent space. Like the tangent space is naturally understood to be the column space of the parameterization. So to find the perp to the column space of the parameterization, the Jacobian of the parameterization, of course, you just calculate the null space of the transpose of the Jacobian. So that rings true. Anyway, I'm going to go on. Let's focus on the linear algebra. I'm trying to focus. So example 2 here. And by the way, of course, I have endless videos on this in my linear algebra if you thirst for more examples with lots more details, but I'm trying to just give some really limited focused examples here. This one actually requires some row reduction, which maybe you should see some of because that's kind of like, you know, a central calculation to know about. Dr. Sprano claims they used to teach this in high school. I want to believe. I mean, I think it could be, certainly. Anyway, so we calculate row 3 minus row 1. That zeroes out this piece here. All right. And then I calculate row 3 minus row 2. It always is based on the matrix right before. So row 3 minus row 2, let's see here. Row 3 minus row 2, that gets rid of this 1. All right. And then I do row 3 over 2, row 3 divided by 2. That's easier. We just divide row 3 by 2. Then I add row 1 and row 3 to put into row 1. That has the effect of zeroing out this 1, and minus 2 plus 3 halves is minus a half, all right? And then finally, one last bookkeeping thing, I switch row 2 and row 3 just so that it's in the proper format to be the quote-unquote reduced row echelon form of A. And there are websites that will calculate the reduced row echelon form of a matrix. And of course, it's also in like MATLAB. You guys, I think some of you guys are engineers. You know the MATLAB. So, yeah. So in this case, there are 3 pivot columns. This one, and this one. And this other one, the one that doesn't have a leading non-zero entry in the rows, right? This is the leading non-zero entry, leading non-zero entry, leading non-zero entry. This one does not have a leading non-zero entry row. That's the non-pivot column. And that will give us the variable that must be present in the null space solution. So we have x1 is 1/2 x3, x2 is minus 3/2 x3, and of course x4 is equal to 0. Now why am I saying that? If you do this, you can, what you actually do more naturally is you think about the augmented coefficient matrix of A with 0 if you're trying to solve AX equals to 0. Right? So like this is what we look at. You want to understand this. This is going to inform us what the solution to AX equals to 0 is. All right? We look at that to try to solve AX equals to 0. That's the augmented coefficient matrix. And the thing is with row reduction is it doesn't matter if you slap a 0 onto the end of it. Nothing happens. When you do row operations, the 0 begets 0 begets 0 begets 0. Every step just moves these zeros amongst each other. So nothing happens here. So what that means is if you're solving a homogeneous problem, that is a problem where you're setting AX equal to 0, not something non-zero, you don't really need that inhomogeneous column. It's kind of extra. So when I just do row reduction on A, it does reveal the homogeneous solution, despite the fact that I haven't technically written down the quote-unquote augmented coefficient matrix. Nevertheless, as we do row operations, we're finding equivalent systems of equations that have, in the same sense that they have the same solution set as the original equation AX equals to 0. So as I do these row operations, I'm basically converting the given system of equations, which corresponds to this matrix, right? Like the first row is like x1 minus x2 minus 2x3 equal to 0. This is x4 equals to 0. This one is x1 plus x2 plus x3 plus x4 equal to 0. So that original system of 3 equations and 4 unknowns, you do the row operations and you find out, oh, it's actually equivalent to this much simpler system, namely x1 minus 1 half x3 equals 0, etc. But these ones we can rewrite in terms of the pivot variables being linear combinations of the non-pivot variables. Here are just x3. And once you have that, you can just write down the solution for the null space, because this is my x1, this is my x2, this is my x3, x4 was 0. We can pull out x3 and we get this ugly vector with fractions. And then we think about our life and we realize fractions have no place in our life. And so we factor the half out to get us a nice, pretty integer valued basis for our null space. Of course, this is not a necessary step. You could use that one too. But anyway, the null space is the span of 1, minus 3, 2, 0. And there you go. Now, again, as a check and an evidence further of my claim, you can see that the basis for the null space is in fact perpendicular to every row in the matrix. And that's not an accident. The null space of A has vectors which are perpendicular to the rows of A. That matters because a big part of our discussion of normal space and tangent space is the identification that they are perpendicular to one another, right? They're perpendicular to one another, and depending on our viewpoint, if we have the implicit viewpoint, normal space easy to calculate. If we have the parametric viewpoint, tangent space easy to calculate. Actually, the other one's never that hard to calculate because the null space calculation's not really a big deal. But it is a calculation. So here's another definition for us. Column space is the span of the columns. The column space of A is, that's called the column space of A. And the dimension of the column space, which is, by the way, the number of vectors in a basis for the column space, that's called the rank of A. And the dimension of the null space, incidentally, is nu A, which means the nullity of A. One of the big theorems of linear algebra, if I can get 90% of the students to understand this and leave my 221 class with this, I feel like I've done a good service to the mathematical community. And when a student doesn't know this leaving my class, it makes me sad. But it does happen. Anyway, so the column space of A has a basis formed by its pivot columns, and for A and m by n matrix, we have the number of columns is the rank plus the nullity. Of course, this is kind of like duh, because the number of pivot columns gives you the rank, and the number of non-pivot columns gives you the nullity. Every column is either a pivot column or a not pivot column, so of course the number of columns is rank plus nullity. But anyway, so here's another example. Here's a 3 by 3 matrix. This notation just means there's row reductions which get you from here to here. I don't want to go into the details, but that's my row reduced matrix. And from that, I can see that columns 1 and 3 are the pivot columns. I have to use the columns from the original matrix for my basis of the column space. So 1, 3, 4 and 0, 1, 1. That'll do it. The rank of this matrix is 2. To solve the null space problem, to find a basis for the null space, AX equal to 0 is tantamount to saying x1 is minus 2x2 for my first row there, and x3, well, apparently x3 is 0. So you put that into the equation, the vector x1, x2, x3, and you get yourself this. You factor out the x2, basis for the null space, minus 2, 1, 0. And of course, not to beat a dead horse, but you might notice that that vector is perpendicular to this one, and that one. All right, not an accident. Here the rank is 2, the nullity is 1, 1 plus 2 is 3. Hooray! And here's another comment I should make. When we're solving, this doesn't really matter to us too much in advanced calculus, but this is just something you ought to know as a student with an advanced engineering or math degree. When solving AX equals to B, the solution has the form x is equal to a homogeneous part plus a particular part. The homogeneous part actually appears as a null vector of A, right? And the particular part is, well, it's actually a solution, AX P equals to B. So in short, the nullity of A indicates the number of parameters needed to form the solution set of AX equals to B. All right, that's the meaning of nullity as it relates to solution sets. Moving on here. Let us turn the page here. The other thing I should talk to you guys a little bit about is eigenvectors and diagonalization. All right, so what I'm going to do is we're just going to define eigenvector, eigenvalue, and we're going to work our way through a particular example to illustrate the program of diagonalization. That's really what we're after. We would like to know what diagonalization is because it gives us a means to take a complicated, ugly formula and put it into its most simple form. All right, that's what this is all about, is making a complicated formula much prettier. So an eigenvalue is simply a scalar which has a corresponding non-zero vector called an eigenvector. I guess I should write that down, U as an eigenvector. Oops. U is eigenvector. All right. And A times U is equal to lambda U. Now, of course, I should also mention, a lot of times we like to look at it like this. A minus lambda times the identity matrix acting on U is equal to 0. That's, an equivalent characterization of the eigenvector. Great. So then, theorem, if lambda is an eigenvalue of A, then lambda is a 0 of the characteristic polynomial. And that characteristic polynomial is defined by taking the determinant of A minus t times the identity. So here's the proof of that. It's not particularly complicated, and here's how it goes. If you have a vector non-zero that solves AU equal to lambda U, that's tantamount to having a solution to A minus lambda IU equal to 0 for some U not equal to 0. But the thing is, we also have U equals to 0 as a solution. And we can't have two solutions for this problem if that inverse exists. See, because if the inverse exists, then you can simply multiply this equation by the inverse matrix and you get only the 0 solution. But we have something more. We have the U not equal to 0 solution. Therefore, the inverse doesn't exist, which is to say that the determinant of this matrix have to be equal to 0. But if that's determinant is equal to 0, that's tantamount to saying that lambda is actually 0 of the characteristic polynomial of A. That's it. All there is to it. Now, so what this means then, as a calculational procedure, is to find the eigenvalues of A. All we have to do is calculate the characteristic polynomial and factor it. I say all we have to do, but in truth, when you get to a 3x3 problem, that does get to be a bit much. But for a 2x2, we can do it, and we won't even break a sweat, especially not today. So 1, 3, 3, 1 is my matrix, which is given the characteristic polynomial I get from A minus Ti, which gives me this. Now that determinant, I like to flip the minuses so I get T minus 1 squared. Just a little algebra trick, all right? Nothing big there, but it saves me a lot of trouble. T minus 1 squared minus 9, that is the difference of squares, so I use the factor like that, which gives me T plus 2, T minus 4, which means my eigenvalues are minus 2 and 4. And so those are going to give me non-zero solutions to this equation. So if you look at the lambda equals minus 2 equation, you got that. If you look at the lambda equals to 4 equation, you got that. It's manifestly clear that the solution to this is 1 minus 1, and the solution to that is 1, 1. Now, indeed, these are not unique solutions. In fact, any scalar multiple of this or that will work, but all we need is one solution for the sake of the current discussion. So these are eigenvectors for A with eigenvalue minus 2 and eigenvalue 4. Excuse me. Goodness gracious. I am losing my stupid voice. Let me drink a little bit. So theorem. If we have a matrix that has n eigenvectors with eigenvalues lambda 1 through lambda n respectively, and it just so happens that if we put all those vectors into a matrix, the determinant's non-zero. Of course, that means that they're linearly independent vectors as it happens. Then in that context, P inverse AP is a diagonal matrix with the eigenvalues down the diagonal. And this is the program of diagonalization. We do a similarity transformation. This is a similarity transformation of a matrix, and we get a diagonal matrix. But there's more. And in fact, pretty much our only application this semester concerns this particular case, which is that the matrix is symmetric. If A transpose is equal to A, then A is actually orthonormally diagonalizable. That is to say that there exists n orthonormal eigenvectors, and for an orthonormal basis, it's the case that the transpose of the basis matrix is the inverse, which is awesome. So instead of doing P inverse AP, we actually can just do P transpose AP to diagonalize. This altogether I would refer to as the quote-unquote real spectral theorem, something that, if I'm doing my job, I would prove in 321, but sometimes I don't do my job. All right, so anyway, it's in our book. So here's example 4 continued. if I had this vector and that vector, these are orthogonal because their dot products are 0, right? But pairwise dot product, this dot that is 0. But they're not normal because this has length square root of 2 and that has length square root of 2. So what we do is we rescale them to unit vectors by dividing by square root of 2, both ones. So then my basis matrix is 1 over root 2, blah, 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 and my transpose is 1 over root 2, 1 minus 1, 1 minus 1, 1, 1. I find when you got a root 2 around, like, it's just better to factor it out as opposed to writing it 4 times in the matrix. Like, you're allowed to work with a number times a matrix. That's a legitimate calculation. You can do that. It'll save you much suffering. See, because the difference between doing that and not doing that is adding a ton of fractions in this calculation below. So be smart. All right, don't be like me. So I factor out the 1 over root 2 squared, that gives me a half, and then here's my p transpose AP, again with the root 2 up front. And so when I multiply these, I get that matrix. And then when I multiply that by that, I get this matrix. And then when I divide by 2, I get that matrix. But lo and behold, that is my diagonalized matrix with eigenvalues down the diagonal. We have diagonalized A by a similarity transformation. Now, you might think I'm too excited about this, and you're probably right. But let's see what it does. Let's see what it does. We introduce a little bit more terminology. Given an eigenbasis, all right, given an eigenbasis, let's call it beta for A, with matrix beta, V1 through Vn concatenated. We define beta coordinates, x sub beta, as the inverse matrix of beta times x. Okay, so like this is true whether or not the eigenbasis is orthonormal, okay? For the bottom part of this theorem, I'm assuming an orthonormal basis. This is true, this part up here is true even when the basis is not orthonormal, like we could always do this. It's just that if the basis is not orthonormal, then it's like a pain. You actually have to calculate the inverse. But anyway, if we assume we have an orthonormal basis, so beta transpose is beta inverse, the matrix beta is the matrix inverse beta, then I can introduce eigencoordinates. Let's say y equals to the beta coordinate of x, and that has the equation x is equal to matrix beta times y. And so if I take this equation down here, which we'll soon identify as the formula for a quadratic form, then by the sock shoes principle, I can, product of a transpose of the product is the product of the transposes in opposite order. So I get my y transpose beta transpose A, beta y, but hey, lo and behold, that diagonalizes A into this, which means that if you use eigencoordinates on the quadratic form, you get this formula in eigencoordinates. Instead of having this possibly rather ugly formula in x1 through xn, you get this beautiful sum of squares formula in the yn's, y1 through yn squared. And this formula is much easier to interpret in matters of application. And it actually reveals interesting questions, interesting answers to questions you could have raised as a middle schooler if you were curious and not beaten down by the man. I'm sorry, maybe you're a homeschooler, so I'm just talking about disrespectfully about your mother or something, but my apologies. A quadratic form on Rn is a function from Rn to R for which there exists a symmetric matrix A such that Q of x is x transpose AX. So like, for example, we can look at example 4 as a quadratic form kind of thing, because if I take this row vector times that matrix times this column vector, lo and behold, I have this formula, x1 squared plus 6x1 x2 plus x2 squared. This is a quadratic form in x1 and x2. It's quadratic because every term is like second order. Now, if I make the if I use eigencoordinates y, like I was saying, if I make a substitution of x1 is y1 plus y2 over root 2, and minus y1 plus y2 over root 2, if I take star star and plug it into star, then what will happen is I will get the much more beautiful formula, minus 2y1 squared plus 4y2 squared for q of x. You might say q of y here. It's kind of a matter of, well, actually that's not correct kind of thing. But if you understand what q of y means, technically speaking, I really have to write a composition of a function I haven't named to make that mathematically accurate, but I feel like I should stop talking about that, as it would not serve this purpose of this lecture. All right, so moving on. Example 4 continued. We have this here, if we trade notation x1, x2 for xy, and we trade y1, y2 for x bar, y bar, as I often do, then what's going on is you start with Cartesian coordinates x and y. We've had this expression x squared plus 6xy plus y squared. When we put it into eigencoordinates, we get minus 2x bar squared plus 4y bar squared. So if you think about that, if I was to give you x squared plus 6xy plus y squared equals to 1, I don't think anybody would have known what that was without, like, using software or something. Like, just off the top of your head, what does it mean if you have x squared plus 6xy plus y squared equal to 1? You wouldn't know, right? But we can calculate by finding eigencoordinates. It becomes clear if I put this equals to 1 in the x bar y bar coordinate system, well, by golly, that's a hyperbola. And I can even graph it because here's the x bar points in the v1 direction, y bar points in the v2 direction. And so you see what we really have is simply a rotated hyperbola. So all of these conic sections in the plane that involve cross terms, they're basically just rotated conics. And the rotation by which they've been rotated can be uncovered by simply finding the matrix of the quadratic form, finding the eigenvalues, the eigenvectors, and performing the requisite rotation. Really good calculus books of yesteryear had this stuff in it. I don't know if a mainline calculus book right now has it in it. We're getting dumber. Anyway, so don't worry, AI is going to fix it though, because AI knows. It probably does, actually. But anyway, so essentially here's the deal. If you have a quadratic form on R2 with a matrix A and you know that its eigenvalues are lambda 1 and lambda 2, then you can completely specify what the graph looks like just on the basis of the eigenvalues. If you think about it, both the eigenvalues positive, it's an ellipse. Both the eigenvalues, the product of the eigenvalues negative, it's a hyperbola, which either opens one way or the other, depending on which one eigenvalue is positive and negative. If either one of the eigenvalues is 0 but not both, if you think about the equation that gives you, it gives you like, it gives you basically, let's say lambda 1 y1 squared equals to 1, right? So that just gives you y1 is like, plus or minus 1 over the square root of y, square root of lambda 1. So it's a pair, in that case, a pair of, I'd say horizontal, but a pair of lines, because the eigencoordinates don't have to be horizontal, like y bar was like this up here, right? But anyway, so it gives you a pair of lines if one of them 0 but not both. Of course, if they're both 0, there's no solution, because both eigenvalues being 0 forces the quadratic form to be 0. And if they're both negative, you got no solutions, because you'd have a minus a square minus another square equals to 1, which is of course an impossibility for real variables. So in summary, when we're faced with a quadratic form, x transpose A equals to x, right, with A transpose equals to A, we can diagonalize via eigencoordinates into the much simpler formula of star. Then questions about the quadratic form become much simpler questions about this formula. And for R2 or Rn, this amounts to rotating a nice coordinate system which uncouples the formula for q of x. Uncoupling is the idea that you're removing the term which involves both coordinates, like this xy term. Over here, you've got x bar squared, you got y bar squared. You've got nothing that simultaneously involves x bar and y bar. It's uncoupled. You can think about x bar and y bar separately. That's uncoupled. Now, let's cycle back to advanced calculus at this point. Yep. Hit a little sip of something. We got, what we got? Here's a multivariate Taylor series. Yay! 47 plus this and that and that and that. If you look at this, there's no first order terms, which means that the gradient at 0 is 0. So by inspection, 0 is a critical point. And okay, so I can look at the Hessian, I can look at the quadratic piece in the Taylor expansion, and I can understand it has this matrix A. And if I calculate the characteristic polynomial for that, this is just a slight twist on example 4, guys, because basically if you look at it, it's just got 8 adjoined to the matrix we just studied. And it turns out then that you have the eigenvalues that we already had, minus 2, 4, and now 8. All right. And as such, if we use eigencoordinates, we can put this formula, we can put the multivariate power series for the function which we have given into eigencoordinates like this. Z bar is equal to z. It's kind of silly, but it's now clear that f of 0 equal to 47 is neither a max nor a min, because it increases in one direction and it decreases in another direction if you're close to the critical point of 0. A couple more examples for us. Just trying to make sure we understand. Like, this is not complicated, really. It's not. If it's already diagonalized, it's really simple, okay? Here's another one I made up. So if we look at a squared from example 4, we get that. It's not an accident. The square of the matrix, you square the eigenvalues. Like minus 2 squared is 4, and 4 squared is 16. So you can check it out. This actually has eigenvalues 4 and 16. And if you look at, if we're given a function that has this as its multivariate, bivariate power series expansion, this time centered at 1 minus 2, it's evident that 1 minus 2 is a critical point because there's no linear terms. So the gradient 0, and if we look at the quadratic form, we have this, which by the theory I just told you about, in eigencoordinates becomes 4h bar squared plus 16k bar squared, which reveals to us that, in fact, the critical point here is at actually a local minimum, because we have an expression which, if we're close to the critical point, necessarily gets larger if we go away from 0, 0. Here's an example. I wanted to at least give you one example where we didn't have a critical point, because that's kind of part of the course, and it's not hard either. If we have a linear term here, I can read from that fx is 3, fy is, there's no y term, 0, fz of 0 is 0. Now fxx is 20 because there's like a half in the formula for Taylor expansion, and it turns out that fxy is minus 6. There's a distinction between the way mixed variables and repeated variables behave, because in some, well anyway, I'll shut up. 8z squared shows me that fzz is actually equal to 16. So when I look at the Hessian matrix, which actually has 1/2 partial I partial j f at the point in question of expansion, which in this case is 0, 0, 0, I get this matrix. 10, minus 3, 0, minus 3, 0, 0, 0, 0, 8. Notice that we have to half whatever's on the mixed term, we take half of that to put in the matrix. You want to make sure that you keep the matrix symmetric, because then we get the beautiful real spectral theorem and things work out so nicely. I guess I just have a minute left. Let me take a gander over here at the notes. Try to wrap this thing up here. Where am I? Okay, so I have all these exciting formulas for multivariate. So here's the actual multivariate power series. Eventually I have that over here. It's like, there they are. Those are the multivariate power series in all of their glory. Really cool stuff. But, oh goodness, yowzers. And I do some routine calculations in here. So then I have this, introduction to quadratic forms. I've basically showed you this is what I did today, is I showed you essentially the linear algebra of this. So there's some more like entry-level examples in here, which are probably good for you to read, right? Like if I have oopsie, this, then I can read that's the matrix. If I have this, then I can create that matrix. So, this, I think it's helpful. A couple examples like that. Now, there's, some terminology, negative definite, positive definite, non-definite. It turns out for a quadratic form, whatever it does to the unit sphere, it does everywhere else as it happens. This one, here's the graph of z equals to x squared plus y squared. It's a paraboloid. Here is the graph of z equals x squared minus 2y squared. It's a hyperboloid, I think. Here, it's a saddle point, of course. This one is z equals to 3x squared, which is a parabolic trough, I believe. And, here's the quadratic, some level surfaces of the quadratic form x squared plus 2y squared plus 3z squared. Now, I introduce, of course, the eigenvector, and we go through the stuff I just went through, and I have some sample eigenvector calculations over here. Great. Really hoping to get something before I run out of time here. And perhaps interestingly, I actually have some examples where you can see the eigendirections, the rotation of the thing to reveal the the rotated parabolic trough or whatever. Here's a rotated saddle. And finally, at the very end I have a rotated ellipsoid. So again, the eigenvectors reveal it. But I guess that's a wrap for today. I think next up we're doing